Okay, so where did I? So this is where I got stuck yesterday. Okay, so so the point was to explore the applications of what I called the gradient test, I suppose, good way to call it, which is a simple corollary of Claudeur's theorem. So mixed derivatives are equal, mixed second derivatives are equal when the function is well behaved, and then if our vector field is the gradient of some well behaved vector field, then it has to satisfy, its component has to satisfy a certain identity, and that is the identity. This is the identity over here. So that's the what is supposed to be tested in order to verify whether or not it might be a vector field. Okay, so we already had a couple very simple ones. So this is dimension 3, so we're not going to do it. As you can see, way more work. Here we looked at this vector field before, and remember we tried to find its potential function, and we failed. Not just failed, but by inability to do it, but rather we discovered that there is no such thing. Okay, so then the conclusion was no, it is not a gradient vector field. This time around, all we have to do is way simpler. We just look at the derivatives, the cross derivatives. So the x component, that y is the x component. We differentiate with respect to y, which gives me 1, and I differentiate negative x with respect to x, which gives me negative 1. They don't match, and so that we conclude that no, it is not a gradient vector field. Okay. So the next one, I proceeded. And then before that, for a while, I also was pointing out at the rotational nature of those vector fields that might not be gradient, because rotation, making a full circle along the gradient, should not bring you back, because of that result, to be proven. That we are climbing the value of the function if we're moving along the gradient. Okay, so if these are the gradients of a function, then we cannot make a full circle. Okay, so so that's example. The first example is exactly that. So we showed that it is impossible. But then let's try to modify it slightly, which I did next, and I normalized the vector field, so made all the vectors unit. Okay, so the differentiation produced, I didn't take all the way through, but you probably can see that things do not work out in the sense that these two still don't match. So, yeah, well, if you just carefully look at it, so what is that? I have x squared plus y squared minus y squared over square root of x squared plus y squared over that fraction in this same denominator and this same first term, but the second term is different. And there is a negative sign over here. Once again. So as you can see, these two functions are unequal. Okay, so once again, the conclusion is, for this one, the normalized rotational vector field, that this is no, once again, not a gradient vector field. Okay, and furthermore, and then, so that really not a big point, then it's still bad, but it turns out that if we do it slightly more than that, and if we divide by, not by the square root of x squared plus y squared, which is the length of the magnitude of the vector, but rather by the square, well, then things work out differently. So I'm defining vector field u, xy, 1 over x squared plus y squared, and here I have the same vector field as the original y negative x. So as you can see, what I'm doing is I multiply the vector itself by a scalar, which means that the direction doesn't change. So it will look exactly like this, but this time, so here the blue was v, the original vector field, with a lengthening of vectors as we move away from the origin. The red one was this, the normalized vector field, so that's w. Okay, and now what I'm doing is, what do I do to, what have I done to the vector field, the last one? what does it, oops, what does it look like? So, like I said, the direction will be the same. It still will be going around the circle and will be kind of tangential to the radius. But what is happening as we're moving away from the origin?
The magnitude is going to zero.
The magnitude will be declining and fast like this. So, yeah. So it is rotation. I don't think I'm doing rotation in the right direction. It's going in the opposite. It goes x is equal to y. So it's actually it's counterclockwise. So I'm afraid I made that mistake twice. So they're supposed to point in the opposite direction, like this. But otherwise, they are rotational. Okay. So, and here what I'm trying to say here is that they are pointing like this. So 1 then will be less and less and less. And here, same thing, small and smaller. And bigger and bigger as we approach. I don't want to draw it here, but you can imagine that this way. These vectors are bigger and bigger. So they are around the origin. We have actually infinite limit. So in fact, it probably makes sense to state both of these facts simply from examination of the formula. These are the conclusions. Number one is that the magnitude of vector u of xy, okay, it will go to 0 as xy goes to 0, okay, it goes to infinity. So now no matter in what manner, if we're moving away from the origin, the magnitude diminishes. And on the other hand, number two fact is that if we're moving towards 0, we are going, the magnitude will go to infinity. Okay, so it is a bit, so you will going faster, closer to the origin. So really faster and faster and faster. But it's still purely rotational, so it's not a whirl. I don't know any magnitude here. I just say xy. Xy goes to 0. Okay, so these are the two facts, and now let's apply the gradient test. So I'll be doing partial derivatives of the two components. The first one is y over x squared plus y squared. The second one is negative x over x squared plus y squared. That is my vector field. This is P, this is Q. And we differentiate P with respect to y and Q with respect to x, cross multiplication. So dP dy is, okay, so similar to last time. But so I differentiate with respect to 1 and then multiply by the denominator minus y, the numerator, multiplied by the derivative of the denominator, which is 2y, right? So there is no fraction as last time. Okay, so derivative of the numerator 1 times x denominator x squared plus y squared minus the numerator multiplied by the derivative of the denominator. Just keep in mind which of the two variables. Okay, so I could simplify it into what? X squared minus y squared. The numerator, that's what the numerator is. Okay, and now I do the other one, dq dx. Everything is similar except minus sign in the beginning, so I'll have negative 1 x squared plus y squared plus x times the derivative of the denominator, which is 2x, over x squared plus y squared squared. Okay. So and then this gives me once again x squared minus y squared. they're equal. So what's the conclusion?
U is the gradient of the vector field?
No.
U is the, it is a gradient vector field.
No. Look at the theorem again. What's the conclusion? So this is satisfied, right? So what's the conclusion?
Well, I mean, we don't know that it's a gradient. You know, if we know that A implies B, we can't say B implies A. But
Well,
we know-
that is the conclusion.
Okay.
So all we can say, it's not very profound what we have found. What is it? What we have discovered. It passes. So the gradient test is passed by this vector field. Okay, so I put the exclamation point and then I say, so what? And the answer is nothing, because we cannot draw any conclusion from it. And if we could, then the actual question becomes, then we ask ourselves, does the converse of the gradient test true? So if we want to actually do anything with this information, the question is the converse of the gradient test true? Okay, so in other words, if the equality dp dy equal to dq dx satisfied, then does it imply that PQ, that vector field, is gradient? Okay, in the we'll show that under certain circumstances it is true. Certainly, we actually, the fact is, however, even if this was true, which is still to be discussed next after the break, turns out that this is still not a gradient vector field. So apart from this, so it's a fact to be discovered once again. So two things that we'll still have to discuss to show the converse, in what sense converse is true. And then the other fact, and then seemingly contradicting fact, is that this is not a gradient vector field. So the U, so one is this is true in some sense, but on the other hand, U is not gradient. Okay, so yeah, like I said, two seemingly contradicting facts to each other, because the U passes the test, and if we read this as it's stated, it appears that passing the test gives you gradient vector field, but not always, not in that sense that because why? Because the caveats are missing. There are those conditions that you impose on your statement in order to be true. Well, if you skip them and only concentrate on the punchline, then you might be losing something big time. So one, it is not very hard to justify why it's not the gradient vector field. I have done it before, again, because it is rotational. So if it is rotational and you follow, so suppose it is a gradient vector field, there is a function, the gradient of which is u, and then you end up climbing, you follow gradients and then you come back. But if you follow the gradient, you're climbing the function, so you cannot come back. So that's roughly how you explain why it cannot be the case. We certainly will make it more specific how. That is why we started this next topic of integrals, because the following paths of like this, for example, if we're going along the gradient, then should tell us if are we climbing or we're not climbing. Is it possible that the vector field that we're looking at actually produces a function at some point? So that is still to be discussed. So right now, all we have is that this vector field has passed. There are both, three categories. The gradient vector fields, the non-gradient vector fields that pass, the gradient yes and no that do not. The difference is why this discrepancy between these two. I can actually point my finger at where the problem is. Here it is. Right here. This is the problem. Well, that's what creates the difference. Creates the difference. What's so special about this point? Here.
It can't have a direction.
No, it's not that it cannot. It doesn't. Our vector field is undefined. Okay, so it is the U is undefined at the origin. So the domain has a hole in it, and that's a big deal. In dimension 2 especially. In dimension 1, remember that if you had a hole in the domain of a function of one variable, so the situation was like this. It is not a big deal in the sense that you sort of have two different universes happening to the left of the hole, to the right of the hole, and they do not interact in any way. Okay, so it was a problem in a different way. Okay. But because there was a line. Okay, now we are on the plane and missing missing a point in the domain, it creates a totally different situation. It creates our ability to make circles around it, and that might create some problems because of that. So we have not broken our domain into two unrelated pieces. It's still one piece, and then yet there is a hole there. It's like a what was it similar to? So making a trace like you can wind like a piece of rope around the pole, okay, and then you cannot pull it up. You make a full circle, and then your string is hung on the pole, and you cannot pull it off. So I'm talking about topology. What's called topology of properties of spaces that is unrelated to distances, but rather only studies properties of those spaces that are preserved under continuous transformations. So for example, if you take a piece of paper with a hole in it, you can crumple it and you can even stretch it if you can, but the hole will not go away. Okay, so that's topological thing, and it is the topology then of the domain space determines a lot about what kind of calculus you're facing, and that's the difference between one-dimensional calculus and say two-dimensional calculus. And then think about it: what happens if we move to three-dimensional calculus? What happens if you remove one point from the three-dimensional space?
We have a line this?
No. If I said remove a point, it will be different from either dimension 1 or dimension 2. You cannot wrap a rope around a point. You can, if you have a plane and you have a pole there, you can wrap it around it, yes. But if you are in a three-dimensional space, there is no such thing. So the curve will be, you can wrap it around the point, but then you can just pull it off, and there is nothing. So there is no such thing as a three-dimensional pole. It's or a three-dimensional hole is really very easy to avoid. So as you can see, dimension 1, the hole is impossible to avoid. You break the whole space into two. In dimension 2, you can easy to avoid it, but if you make a circle around the point, your life kind of changes. If you imagine that you have once again, maybe you're a dog, and it takes a trip around that pole, then it cannot go away because there's a hole, there's a loop there. In 3D, that doesn't happen anymore. Once again, if it's just a point there, like literally like a point, then all the curves walk around it, and you can pull that rope off, and nothing is happening. So these are topological issues that affect the calculus that in different dimensions. Okay, so two-dimensional, as you can see, kind of awkward in that sense. But it means that if you move to third-dimensional, that you're not to have the same effect. You won't be talking about curves, but you're talking about surfaces. Okay, so if a point is removed from the space, and then you have a surface, and that point is inside of the surface, then that surface cannot be pulled off, just as you cannot pull off a curve like this. Okay, so you have a curve, and then if the space has a hole in it, you cannot pull it off. In 3D, then you will be talking about surfaces. Anyway, so that certainly is a vector calculus issue, but what we have left is that a big problem of a big statement about, so this is still to be continued, but what we need to really take care of is that the claim that we are moving up the hill when the direction of the fastest growth is the gradient. So let me. Okay, so let me put it in words first. So the gradient is the direction. It is a vector, so it gives the direction of the fastest growth of the function. Okay, so all good. It sounds very convincing. We have seen all the examples. They suggest exactly this fact. Okay, so remember, like this. If these are level curves, then we're going like this, and we are definitely climbing. So if it's 100, 200, 300, then which way do you go? You go perpendicular to those level curves. But that's now is not good enough. And we want to make it a precise statement and prove it. Okay, so the gradient of the direction, so we have f, a function of several variables, say is equal f of x capital. Then we have our vector field f del f. Okay, and we fix a point. So this is one point at a time. That helps. I don't want to look at all the points at the same time. So I'm looking at one particular point, a capital, and I'm looking at the vector b, which is del f of a, okay, and then now I'm just that part is okay. The gradient of the vector field now, what is direction is also understood. We also know the function, but what does it mean? The fastest growth of the function. That is the questionable part. The fastest growth of the function. What does it mean? Out of all directions, that we could understand that there are infinitely many directions from this point, and one of them is supposed to provide it with the fastest growth. But once again, what does that mean exactly? So we know how we're studying this function f, okay, and we have already demonstrated that a very powerful way of studying a function like that is to look at the parametric curves in the domain. Okay, so. So we're taking trips. We're taking trips, round trips or any kind of trips, or along what we did this week, trips along the level curve. That's especially nice. So remember like this. So staying on the same level. That was a nice trip. Especially doesn't take any effort because there is no climbing. Okay, but now we are sort of interested in the opposite way. Way of looking at it, because we now want to compare all the possible directions. Well, by the way, it's so there will be no confusion. I am talking about the curve itself lies that we're going to use lies in the domain of the function, not in the three-dimensional space. So technically, what I'm looking at is this curve. So this is the parametric curve that we're studying. It is in the xy plane, while this is the z-axis gives you the actual value of the function. So parametric curve. So take parametric curves starting at x equal a. Okay, so once again, we have our xy plane. This is the point A, and there are infinitely many directions to be taken. And how do we take those directions? We take them with parametric curves. And then we'll compare the rate of growth. The rate of growth of all the directions will be compared to each other for different parametric curves. So as you can see, so these are the parametric curves that I have in mind, these. And that's the good news is that it doesn't have to be this complicated if we're talking about parametric curves, but we only care about directions in particular, how fast you go in the particular direction. Then there is no point of taking all parametric curves. How about we just take straight lines? So limit f, curves f, to straight lines. Then there will be one vector per curve, almost. So suppose, let me delete this. Suppose we pick a vector v, and then we just have a parametric curve in that direction. So v will be our direction vector. And just write the point slope formula. The point being A, the slope being B, not technically the slope, but rather the direction vector. So it will be, what is it? F of t equal to A plus what? Well, we don't really need point slope formula as much as we could have our time to start at 0. So how about I just put it dt? Okay, so that's a point passing through the point A at time 0 and goes in the direction of vector v. Okay, so this way every vector v that will give me a different parametric curve. Now, what we also want to do is to, if we want to compare the rate of growth in different directions under this function f, we limit even more. So limit f to these straight lines with unit direction vector. So simply the magnitude of v is equal to 1. So there would be no confusion. I mean, maybe there are two directions and I go fast this way and slow that way. That certainly will make it impossible to compare these two directions. So if we choose our horizontal speed the same, and the two people driving at the same speed in different directions, we can compare how fast they're climbing, and we will know which direction is the fastest. Okay, so the choice is the unit direction vector. And then now what is exactly the rate of growth of f in the direction? It is a familiar thing. It is the composition. So if I take that picture that I have over there, and just so this is my direction v, okay, and then there is the graph of my function z equal f of x. Okay, so this is my point A. This is a unit vector v, and now I'm taking the composition, and as we just did a couple of times this week, h of t is equal to f of f capital of t, which gives me how the elevation of our elevation is function of time. Okay, so once again, we're taking these trips. Our parametric curves are just what we draw on a piece of paper, which is our map. And then when we actually take the trip, we also have to climb or go up or down. So in this particular case, what is going to look like this. This is my parametric curve. Okay, parametric curve composed with it. So how should I put it? So this picture certainly doesn't show all of what's involved here. So it does show to begin with. It shows you it shows you f. Okay, so this is f. Even if we only take in one, we don't really need the whole thing. It also shows you the function 0 of x. F is only showing the path. That is not the graph. It is once again, it is just the path of our function. And then what is this? It's not technically h. What is it? Well, it's actually hard to tell what it is exactly. It gives me h, but in a kind of indirect way. So if this is my graph, z and x and y. Okay, so this is how roughly it works. So let me try to visualize the composition. The value of the values on the z-axis are the value of h. So for example, this is h of 0. Okay, h of 0 is on the z-axis. So from that point A, we go from A to graph of f, and then to the z-axis. That will give me h of 0. So it is. I hope it is. You will recognize this as something that we have done before. Except this composition was last time studied when we followed the level curve, and this function was constant. This definitely is not a constant. In fact, we are considering all possible directions. These entirely arbitrary vector, and so we have to look at those curves or straight lines simultaneously, all of them at the same time. Okay, so and we already know what to do with it, right? We know that we are interested in the fastest growth, so we are interested in the growth of this function, or the function h. So there's a trip that it depends on the location was fixed, the direction was chosen to. We created a straight trip on our map. We draw a straight line, right? And then we took the trip. We climbed the mountain, and we were recording our altitude at this time. And in particular, in the very beginning, in fact, our interest is one particular point. So in the very beginning of the trip, how fast we were climbing. That's the whole question. And you realize that this is about the derivative. So h prime, and we're using, naturally, to differentiate this thing. The chain rule, so it will be f prime of f, I'm sorry, let me use the gradient notation here. Del f of f capital of, well, let me just put a there. Okay, a times f prime of 0. It's just particular, with a very particular straight line that everything starts at 0, and f prime of 0 is, in fact, so these are, remember, this is two vectors, and the dot stands for the dot product. Okay, so this will be still del f of a, so that's our gradient evaluated at this point, which is unrelated to the vector v, but the second vector is v. So if I go back to the xy plane, and this is my point A over here, and we are moving somehow this way, by vector b. Okay, so and then let me plot the gradient somewhere. Say maybe this is the gradient, del f a. Both of these vectors are in the xy plane. And it turns out that the dot product of these two is the how fast we are climbing. So once again, we started our trip in this direction, while the gradient of our terrain, of the function that represents the terrain, goes this way. Okay, so and then we have discovered by the chain rule the rate of growth, rate of our climb right here in this direction is the dot product of our vector and the gradient. Okay, so you certainly can go back to the. Can you go back? You can certainly recover that result we discussed yesterday. It is what if we are actually following the level curve, and then we realize that these would have to be perpendicular. But this time we want to look at them all simultaneously, and we want to sort of classify or evaluate h prime of t in terms of v. This one is fixed. This one is fixed, and h, but h at the same time, this one depends on v. Okay, so we vary v. We rotate v, imagine that v is rotated, okay, around, and while delta f is fixed. And we're examining this dot product and see where is the largest. So that's what we're looking at. We're pretty much asking ourselves, maximize this over all these. Which value of e would produce the largest value of h prime? That's how we understand these words, fastest growth, the direction of the fastest growth. If p will be the direction, and the growth itself will be h prime. Okay? So how do we maximize it? Looking at in other words, now, how do we maximize the dot product when one of the vectors is fixed and the other one has a fixed unit magnitude? Well, we used something for a while ago, the formula for the dot product. Remember?
It's the, so we just want to, we're concerned about the component of the gradient that's largest?
No, h prime literally is what we want to maximize. H prime, which depends on v, so not on t, right? I'm sorry, I probably, we don't really care about t. I want to put 0 here. It is a number on left. On left, we have nothing but a number. But it depends on v. v varies. Nothing else varies. So h prime of 0 for different f's gives me different h's, and it gives me different h prime of 0. And that is what I want to try to maximize. That number over here is the rate of growth of the function in the direction of v, also known as the directional derivative. Of f in the direction of v. Okay, we'll skip that as particular analysis of the directional derivative, but because we already have everything here, we can just continue on and solve the problem. We only the point of directional derivative is in fact then to explain this idea. What does it mean to have a particular rate of growth in a particular direction? That's the meaning of it. And okay, so there's a formula for that product. Remember the kind of algebraic formula for the dot product. What is it?
It's just the sum of the component, the product.
No, that's the definition. The formula in term which involves the magnitudes. Now what? I guess I'll have to write it out here. Say u dot v is equal to u magnitude v magnitude times
Cosine of the angle.
Cosine of the angle. So angle between them. So that's the formula I'm using. And so what do I get? Then I'll have the magnitude of the gradient at that point times magnitude of v and times the cosine of the angle between v and del fa and the gradient. Well, fortunately v is 1, so that certainly helps on one hand. On the other hand, this one is fixed still. So it is the same point, same function, so the gradient has the same value. So then the only thing that we care about, the only thing that determines everything, is the angle. So the angle is the only thing that matters, which we knew anyway. Right? So we know that you run through all the directions, and you know that you know which one the only direction matters. Okay. So our design was correct. giving mathematical meaning to this informal sentence of the fastest rate of growth. It works out correctly, so it depends only on the direction. But now the advantage is then the cosine alpha is in fact a very simple function to maximize. The max of cosine is attained at what value of alpha? What?
0.
That's right, 0. There you go. So that's pretty, and it is, the value is equal to 1, but the point is that, so the max growth rather than decline is when v has angle of 0 with the gradient, which means they're parallel. Not parallel, but rather the same direction. So it has the same direction as the gradient. Okay, so once again, if this is my gradient, del Fa, and I have tried, all these have been tried, I have a whole circle of directions for V. I checked them all out now and tried to maximize that expression, which has been simplified, and we realize that the V that we care about is this one. This one is the best. So it doesn't say anything about magnitude of V because the magnitude of V is 1 anyway. So we're only saying that the direction should be chosen to coincide with the direction of the gradient in order for us to maximize at that moment of time, or at that location, the fastest growth. And then for one is you can tell the another question: what's the minimum? What's the minimum?
Alpha equals pi over 2.
Fine. Negative 1. So cosine is between negative 1 and 1. Maximum is 1. Minimum is 0. I'm sorry, negative 1. So, and it is a minimum at alpha equal pi, which means that it is the opposite direction. So this is the worst minimum. Okay, so naturally, I didn't do a good job here, but they're naturally in the opposite directions of each other, and we are then climbing. We choose to climb either up or down, and this is how roughly it works out. We can also say what that value is. What is the maximum? We know which direction gives you the maximum value, but we also say what is the maximum rate of growth. And from the formula, right here, it's here, right? And we picked alpha so that cosine of alpha is 1. So then the answer is simply the magnitude of the gradient. Okay? So, all right. So that works out. So direction is in direction of the gradient, and how fast we're actually moving, the answer is the magnitude of the gradient. Okay? All right, so I guess we'll just continue after the break. Find time for your project, and give me a call if you need help.